In this biodemographic short, I show that redundancy increases systems reliability. Reliability theory from engineering can be applied to failure associated with demographic aging in living organisms. The reliability of a system in series, denoted SS, with independent failure events of the components, is the product of the reliabilities of the components, where P1 to Pn are the reliabilities of the system's components. The reliability of a parallel system with components of equal reliability P is given here, where N denotes the number of redundant units in each component. Failure models in systems engineering possess three important properties. One, a system constructed of non-aging elements behaves like an aging object, where aging is a direct consequence of the redundancy of the system. Two, at the very high ages, the phenomenon of aging apparently disappears. And three, the systems with different initial levels of redundancy will have very different failure rates in early life. However, these differences disappear as failure rates approach the upper limits. This means that in a system in series, all of the components must succeed for the system to succeed. But in a simple parallel system, only one of the units must succeed for the system to succeed. These diagrams show that redundancy drastically increases reliability. Each circle represents a component required for a system function with a failure probability of 0.3. The logical schematics for four three-component systems are A, series with reliability probability of 0.343. B, two systems in a series with reliability probability of 0.569. In other words, at least one of the two systems will not fail. C, a parallel system with a redundancy of 2 with a reliability of 0.754. And D, a parallel system with redundancy of 4 with a reliability of 0.976. Two additional points. First, note that the same number of components in these two systems, but the reliability is increased from 0.6 to 0.75 by arranging the components in parallel rather than the two series systems. Second, by viewing failure rates rather than reliability rates, we see that doubling the number of components in a system D decrease the failure probability by tenfold between the two parallel systems.